Okay, now that we know what forms when plates collide, pull apart, and slide past each other, we're going to go into a little bit more depth on earthquakes and volcanoes. So our essential question for the day is, why do most earthquakes and volcanoes occur at plate boundaries? So this is our learning target 25. Identify the constructive, these are things that benefit the Earth's surface, and destructive forces, these are things that do not benefit the Earth's surface, associated with volcanoes and earthquakes. Okay, so we're going to first start talking about volcanoes. So volcanoes, there are three different types. There's a shield, composite, and cinder cone volcano. A shield volcano has low silica content in the magma. Silica is a compound of the elements silicon and oxygen. When there's a lot of silica in the magma, then you have explosive eruptions. The shield volcanoes do not have a lot of silica, so they're very quiet. Pretty much what they do is they just erupt layers of lava that moves very slowly. Now, however, these layers of lava can cause floods, which we call flood basalts, and that can be a destructive force on Earth, so that can actually harm Earth's surface. Shield volcanoes cover large areas because they're very broad and wide, so they cover large areas. Examples of shield volcanoes: Columbia Plateau, Mauna Loa in Hawaii, the Galapagos Islands that we watched a movie on, and then Olympus Mons on the planet Mars is actually the largest volcano in our solar system, and it's a shield volcano. The next type of volcano is your composite volcanoes. These eruptions really depend on the silica content in the magma. They can either have a lot of silica or low amounts. So they're either explosive or not very explosive. When they are explosive, they release large amounts of gas and dust, which we look at and call a pyroclastic flow, which is what this picture right here is showing you. So when a composite erupts violently, it emits a large amount of dust and gas into the atmosphere above the volcano. It then starts to erupt lava. So this composite volcano is made up of alternating layers of lava with gas and dust. So that's why if you look at a cross section of a composite volcano, these different layers are cooling and hardening of lava, and then the compaction of gas and dust that comes down. So that's what a composite volcano looks like. Examples: a lot of volcanoes on our west coast are composite volcanoes. So Mount Rainier in Washington, Mount St. Helens in Washington, and Mount Hood in Oregon are all composites volcanoes. The next type of volcano is a cinder cone volcano. Now, cinder cone volcano always has a lot of silica in its magma, so they're very explosive. Because they're very explosive, they have really steep sides, so they're very narrow volcanoes. When they erupt, they throw a lot of lava and rock into the air, and that's called tephra. So, small one. What I'm going to show you right now, this is this link is on my website. You guys can actually play around here. You can change the silica content. Okay, so if you change the silica content 45%, it'll tell you it's a shield volcano. Okay, then you can erupt it. Find the eruption button. Okay. Why won't it erupt? Oh, I think you just have to change. If you start increasing the silica content, it changes the type of volcano below, and then it's going to start changing the type of eruption that you see. So this link is on my website. You can play around with it, change the silica content, and see how that changes how explosive it is. Okay, so back to so that's the cinder cone. Examples of cinder cone volcanoes that we have: Paracutin in Mexico is a cinder cone volcano. Sierra Negro in Nicaragua, and Sunset Crater in Arizona is a cinder cone. Now, if you notice, one of the things about a cinder cone is it usually blows its top off, and what's left is the missing part of the volcano at the top. So it leaves a vent or a crater. And so Sunset Crater in Arizona is an example of that. Okay, so those are our volcanoes. Now, when we also talk about volcanoes, we talk about things that can form when magma doesn't necessarily form a volcano. Magma can form things besides volcanoes. It can form batholiths, dike, and sill. A batholith is just a large area of magma that's cooled, and it's usually underneath the Earth's surface. So if this is underneath the Earth's surface, a large area of magma called a pluton, when it cools and hardens, can form what we call batholiths. A dike and a sill are both vertical and horizontal magma intrusions. Okay, so when magma intrudes into rock layers due to cracks in rocks and it goes vertically, okay, that's a dike. When the magma goes horizontal or parallel to the rock layer, that's a sill. Okay. All right, oh, there we go. And this will show you kind of how, there's our batholiths forming magma, big amount of magma is cooling and hardening, okay? You can sometimes form a volcano. You've got over here, you've got dikes that are going vertical, then you've got sills of magma that are going horizontal. That's the end. Okay, when this cools and hardens, that can form the batholiths. So those are the other things that can form from magma, other landforms. Okay, a caldera is when a volcano blows its top off and a lake forms. So this is actually Crater Lake in Oregon, and that's called Wizard Mountain because part of the volcano still was erupting right there and it cooled and hardened. Okay, another example to show you is when the top blows off of a volcano and water fills up into a lake due to precipitation. And I will show you how this forms. Okay, so here we have our magma chamber. We have a lot of dikes. Here's the volcanic neck that's forming the volcano, and we're going to see how a eruption, the volcano, we got some tephra coming down, some pyroclastic flow, collapse of the volcano because it lost some of its mass down here from the magma coming up and getting released. So it collapses because it's too heavy. There's the Wizard Island. And that's how Crater Lake formed. Okay, I'll show it to you one more time. So when this magma goes through the volcano and there's no more magma left, then it loses some of its mass, and that's why this collapses, because this is heavier and denser than what was below it. All right. So that's a caldera. Okay, so now we're going to switch to earthquakes. Earthquakes occur, remember, during transform boundaries when plates are sliding past each other. Seismic waves are the energy that is generated by the earthquakes. And earthquakes occur around fault lines. Fault lines are where the rock section is actually sliding past. So in a seismic wave, it can cause the ground to move forward and back, side to side, and up and down. Now, when we look at earthquakes, we want to find out where the energy is being released. So where is the section of rock that's sliding past? So here, right here, the fault is the two sections of rocks on either side that are sliding past each other. When they actually move, the point at which they actually move, that's called the focus. Okay, that's where, if you notice all these bands of red, that's where energy gets released. Okay, because remember, these rocks have a lot of stored potential energy, and then when they finally move and slide past, that potential energy gets transferred into kinetic energy, and that's the energy that comes out of the focus. Now, directly above the focus on Earth's surface is called the epicenter. So those are two terms you want to know. Focus is the point where the energy is released. It's always underground. The epicenter is the point on Earth's surface directly above the focus. This is where you'll have surface waves travel out from. And we'll talk about surface waves in just a minute. What's that? Oh, I didn't want to do that. Never mind. Okay, so the three types of waves or energy that gets released from an earthquake are primary, secondary, and surface waves. Primary waves, the rock moves back and forth in the same direction as the wave. It can primary waves can travel through liquids. So if the wave moves this way, the rock's going to move this way. So let me show you what that looks like. Okay, so if the wave is moving that way, that's showing you this is the rock section right here. That's the direction of the rock that's moving. Okay, that's a primary wave. Now, primary waves can travel through solids and liquids. So this is just a picture. Here's a primary wave. This next one below it is a secondary, which we'll get to. Secondary waves, the rock moves at right angles to the wave. So if the wave is moving this direction, the rock is going to be moving up or down and creating a right angle to the wave. Okay, if we go back to our link, let me find maybe it's on this website. Let me check. Same website. Yeah, here it is. So, direction of the wave is going this way. The rock is moving up and down at right angles to the wave. So that's a secondary wave. Now, secondary waves can only travel through solids. Okay, so and that's going to be pretty important when we start talking when we get to this picture down here. Surface waves move back and forth and side to side. So if the wave moves this way, rock will move back and forth and side to side. Okay. Now, the one thing I want to draw your attention to is this picture. So at the beginning of this unit, we talked about the layers of our Earth and how we know when there's a solid part of the lithosphere, and then we go into the middle part of the mantle, the antiosphere, that's a liquid, and the outer core, which is a liquid. Well, how did we know that they were solids and liquids? Well, one of the ways we know is from earthquakes. So if primary waves can travel through solids and liquids, we can measure the speed at which primary waves travel. If you look here, primary waves are in green, and the green can travel through solid part of our lithosphere. It can also travel through the liquid part of our mantle and our outer core. So, but the thing is, it changes speed. Okay, so primary waves will travel faster during the solids and then slow down during the liquids. So we can measure that, and that's kind of how we found out where our solid and liquid layers were underneath Earth. And remember, secondary waves can't travel through liquids. So you see the red, they can't travel through the liquids. So we were able to find out what part of the mantle was liquid and where our outer core was a liquid as well. So we used earthquake data to determine the inside of our Earth. Okay. And then again, a tsunami is an earthquake that occurs underwater. This link's on my website. It pretty much shows you areas on Earth where oceanic plates are sliding past each other and where you can have tsunamis. So these lines right here are where common tsunamis occur. If you want to read more about tsunamis, you can go to this website and it'll talk to you about some of them. Kind of shows you what happens when, see, the plates are sliding past. Okay, creates a big wave. You can measure the height of the waves. Okay. It's not a whole lot of warning on this one. The waves came in. So you can go to that website and look at it some more. You can go a little bit slower. Okay, so how do we know about primary, secondary waves? And how they travel? We use an instrument called a seismograph. The instrument is used to measure, where'd it go? Okay, the seismograph is an instrument that we use to measure and record the time and arrival of a secondary, primary, and surface waves. So that's the instrument that we use to measure earthquake waves. Okay, so hopefully after this you've got a better idea about volcanoes and earthquakes. Remember, if it harms the Earth's surface with earthquakes, they're always going to cause destruction on the Earth's surface, so that is a destructive force. Volcanoes are destructive well because lava will destroy the Earth's surface, so will pyroclastic flows. But also when that lava cools and hardens, it turns into rock, so we actually get a surface again, so that could be considered a constructive part of a volcano. So hopefully after this you're able to identify the differences between volcanoes and earthquakes and how they can help and harm Earth's surface.